Space is for everybody. It's not just for a few people in science or math, or for a select group of astronauts. That's our new frontier out there, and it's everybody's business to know about space. Good afternoon, everyone, and thank you for joining us today. We bring to you Think Again Conclave, the official guest lecture series of Apogee. As a part of the first talk this year, I would like to welcome one of the biggest names in the world of astronomy, an astronomer and a planetary scientist, Dr. Henrythroop. Sir, thank you for joining us here today. We are all very honored and excited to have you with us.
Thank you so much. Thank you for having me here at Apogee.
So, the topic for the talk today is astrobiology, NASA's search for life in the universe, something that cannot help but pique the interest of almost everyone present with us today. But before we hear more on this from Dr. Throop, let us take a quick dive into his very inspiring and amazing life. Dr. Throop has indeed done it all, from being a tea taster to getting an asteroid named after him. He has had a stellar journey so far. Having received his PhD in planetary science from the University of Colorado, USA, his research mainly focuses on outer solar system with his areas of interest lying in planetary rings, planet and star formation, astrobiology, and the origins of life. He's currently working as a program officer at NASA and is also a member of the science team for NASA's New Horizons mission to Pluto and the Kuiper Belt. Moreover, he's the co-discoverer of the smallest moon of what used to be the smallest planet of our solar system, Pluto. Not only that, Throop was also awarded the Carl Sagan Medal for excellence in public communication in planetary science by the American Astronomical Society. His efforts to bring astronomy to rural schools in India and Africa is unparalleled. For his irreplaceable contribution to space sciences and astronomy, asteroid 193736 Henrythroop was named after him. So it is indeed an absolute honor to have you with us. And you're an astronomer who redefined the way we understand space and astronomy. So I would now invite you to enlighten us with your talk.
Thank you so much. It's such a pleasure to be here. I'm so happy to be here at Apogee and at BITS Pilani. I wish that I could be here in person. I couldn't make it this week, but perhaps in the future I'll be able to visit in person as well. So I want to just start briefly. You see that I'm wearing a shirt. I'm not wearing a spacesuit. I'm not an astronaut. I'm an astronomer. So I use telescopes to study the planets. Mostly what I do during the day is using a lot of computers, analyzing data, emailing, doing reading and writing papers. I spend a lot more time doing that than with a telescope, although I do use telescopes and data from spacecraft a lot. I've never been into space. People always ask me if I've been into space. I'm not an astronaut. I've not been into space. I'm probably not going to space. I do get to use telescopes like this one here. This is a telescope in South Africa, with a 1 meter diameter mirror. And so this telescope is one we're using to study asteroid rotations. And I've used other telescopes from around the world to study the solar system around us. I want to just tell you what I studied in the US. I took in secondary. I took lots of maths, lots of science, and I went to university to study a BSc in physics, which in the US is a 4-year degree. Then I got an MSc in astronomy, which is 2 years, and a PhD in astronomy. I should say that there are many postgraduate programs in astronomy in the US and in Europe, in addition to the programs in India. And if you're interested in getting an education in the US or in Europe, you should definitely look at the universities there. Most MSc and PhD students in the US, they get a bursary from the government or the university. That applies to both students from the US and international students as well. So there are many students. I had many of my friends and colleagues who were students who were from different other countries who came to the US for their MSc or the PhD. There's also many students from India who go to Europe, to Germany, to the UK to get their MSc or PhD. And it requires you have to be at the top of your class. These are very competitive programs, but there's many great students at BITS Pilani. And so I know that many of you, if you're interested, there are very good programs to continue your studies. So I'm going to talk about astrobiology today. Astrobiology is just looking for aliens, looking for life in the universe. So when people find out that I am an astronomer, they often ask me, well, do I think that aliens exist? So I'll tell you, The answer is yes, I do think that aliens exist. If you look at the numbers, if you look at all of the stars in our galaxy, there are 100 billion stars in our galaxy, 10 crore, 100 billion galaxies in the universe. You multiply those things together, and there's 10 to the 22 stars in the universe. 10 to the 22 is such a huge number that yes, I think that at least one other star, and probably more, has a planet with life. However, have we ever found aliens? We keep looking for life anywhere in the solar system. We keep looking with radios, we keep looking with telescopes, we keep looking with rovers, and we've never found anything. We have never found life anywhere beyond Earth. We found no aliens on Mars, no bacteria on asteroids, no confirmed radio signals, nothing. So life is out there, but we haven't found it yet. And so that's why we're looking, because we think that it's out there, we just haven't found it yet. The biggest questions probably facing astronomers, the most fundamental questions facing astronomers and scientists in the world is, are we alone? You could break that down. Is our solar system unique? Is the Earth unique? And is life on Earth unique? So let's go back in time. Let's go back to the 16th century, the 1500s. And back then we had a model where Earth was believed to be the center of the universe. And you had the sun at the center, or you had the Earth at the center, and then the sun and the moon and the planets were all orbiting the Earth. And that made sense. We thought that, we are special. People on Earth are the most special. We're at the center of everything, and it's just us here. Then in the 1600s, with the observations of Galileo and the model of Galileo, then Copernicus, we put the sun at the center of the universe. It was orbited by Earth and the other planets. And so you have the sun at the center and then the other planets going around the sun. And so it made us a little bit less special because we know that it's not just the Earth, but there's 4 other planets. The other 4 planets that we could see besides the sun and the moon were Mercury, Venus, Earth, Mercury, Venus, Mars, Jupiter, Saturn. Then in the 1700s, the observations continued, and we saw that the stars, perhaps that Christian Huygens was an astronomer from Europe, and he proposed that all the stars were actually the same as the sun, just further away. So suddenly this means that all of these stars could be very much like our own, further away, the same as the sun, but further away. And this made us less and less special. In fact, it's just us here, but if all these other stars are like the sun, then there's 100 billion other stars out there. So we're getting less and less special with time. Then in 1930, the astronomer Edwin Hubble looked at these spiral shapes. And you can see in this photo, this is the Hubble photo from the Hubble Space Telescope, and everything that you see here is a galaxy. And he proposed that these individual galaxies are just like the Milky Way. And so each of these galaxies has 100 billion stars in it. And so this makes us even less and less special with time. There's our solar system. We're not the center of our solar system. There's our star. We're not the only thing in our star. There's all the stars in the Milky Way. And then there's all these other 100 billion galaxies with their 100 billion stars. And so we're not very special at all. In fact, the universe is huge. It's just all of these other things in there, and we are just a tiny, tiny part of it. Now, when we look more, we see that there are planets probably around all of these planets, or planets around most of these stars out there. We occupy just a tiny, insignificant corner of the universe. Our region is not particularly special or unique. There's billions of other planets around billions of other stars in our galaxy, and many of them may be similar to our own. So we can start to answer these questions. Are we alone? Well, is our solar system unique? Probably not. Is the Earth unique? No, probably not, because we keep finding planets which are similar to the Earth. Is life on Earth unique? We don't know that question yet. We keep looking for life. We haven't found it anywhere yet. So maybe yes, maybe no, but that's the question that we want to answer. So NASA and other agencies have a lot of interest in looking for life, and scientists around the world want to look for life. So what do we look for? What are the characteristics of life? Well, the most fundamental things of life is its complex chemistry. In fact, if you look at the chemical processes that make up life, it's far more complex than any other physical processes that we know. You can look at the most complicated physics in the world, geophysics, the weather, machine learning, quantum physics, galactic dynamics, all of these are super, super simple compared with the chemistry of life. So if you're looking for life, you want to look for something which has complex chemistry. And so if you want to make a search for life, you want to search anywhere in the universe. Let's look for some complex chemistry. What's that complex chemistry going to be? What sorts of things make complex chemistry? Okay, well, one thing that helps is using universal ingredients, ingredients that are really common throughout the universe. So this plot here shows the abundance versus the element. And it shows you how much of each element there is in the whole universe. This is an inventory of the universe. And you can see more than anything, there's hydrogen, and there's helium, and there's a couple of other things. And there's carbon, nitrogen, oxygen. And then the bigger elements get more and more rare. But those most common ones, hydrogen, oxygen, carbon, and nitrogen, these are the most common reactive elements in the universe. And these things, if you put them together, they rapidly combine into millions and millions of different compounds. I'm ignoring helium because helium is a noble gas, so nothing really interacts with helium. And then lithium and beryllium are not very stable, and so you can ignore them. But after those, hydrogen, carbon, oxygen, and nitrogen are the most common, and they go into lots of different chemistry. If you want to make complex chemistry, you can do it in three ways. You can do it in solids, liquids, and gases, because those are the three phases, right? If you do it in solids, if you have a solid, there's not much chemistry that happens in solids. So if you have something which is solid, like an ice cube, the molecules are kind of locked in there, and they don't move around very much. Gases, on the other hand, the molecules are so far apart that they don't hit each other very much, and there's not that much chemistry. So if you have something which is liquid, there's more chemistry that happens in liquid than anything else. So what liquid do you want to use? Well, water is a really common liquid. I mean, look at this chart. You have hydrogen and oxygen right at the top there. And so what happens if you put hydrogen and oxygen together? You make water, of course. So water is by far the most common liquid in the universe because hydrogen and oxygen are the most common elements that do chemistry in the universe. Water isn't stable at every temperature. Like water can't be, if water's too cold, it's going to be frozen. If water's too hot, it's going to be a gas, depending on the pressure. For chemistry, if you want to make complex chemistry, there's a temperature range that you want also. You want to have a temperature range which is warm enough so the molecules, can bump into each other and combine in different ways. But you don't want to be so hot that the molecules break apart. And so if you have a molecule, if you have some life, and you take that life and you put it to 1,000 degrees Kelvin, that's too hot, and the molecules break apart, they burn up. And if things are too cold, then they don't move around very quickly, and you don't form complex chemistry in the first place. So if you do it at the right temperature, and by the right temperature, it's kind of about the temperature that we have in where we are all right now, about room temperature, is maybe part of the sweet spot. So you want to find a sweet spot where it's at the right temperature. So if you want to make complex chemistry anywhere in the universe, here's what you want to do. You want to have the right ingredients, you want to have liquids, and you want to do it at the temperature where chemistry can happen. And so if you put all these things together, we're basically looking for liquid water. So the search for life is basically the search for liquid water. And so that's how you can refine your search. You don't need to search everywhere in the universe for life, for signals. You just want to search for liquid water. And if you can find a place that has liquid water, maybe you have found a place that can support life. Now, you might ask, well, what about the laws of chemistry? Maybe the laws of chemistry are different in different galaxies. Maybe liquid water isn't very common in other galaxies. Maybe there's some other plasma that's in different physics that we wouldn't even recognize in some other galaxy. Maybe we're biased a little bit. But let me tell you a couple of things, which is that from everything we see, it looks like the laws of chemistry and the laws of physics work exactly the same way across the whole universe. You can look at this most distant galaxies that you can find, and you can look at the emission lines coming from them, and they show hydrogen there works in exactly the same way that hydrogen works in our galaxy and in our bodies. And you can look at oxygen there, and you can see oxygen there, and you can see carbon in these most distant galaxies that are 10 or 15 billion light years away. And you can see that their molecules and their atoms work the same way, and they have the same chemistry and the same physics and the same gravity as we do. So the laws of physics are the same everywhere in the universe. Organic molecules, you can find things like methane and water and ethane and so forth, and ammonia. These look alike. We can see these on many other planets. You can see them at Mars, at Pluto, at Jupiter, at Saturn, and so forth. And these organic molecules, they look like they work in exactly the same way on other planets as they do on Earth. So the laws of physics, the laws of chemistry are the same everywhere. And so if you're looking for liquid water, if you're looking for something to host life, liquid water is probably a good bet anywhere in the universe. It's not that it's the only one, but it's a good place to start. So if we want to go to the universe, and if we want to search the universe for liquid water, where should we go? So I'm going to tell you 3 good places to search for liquid water in the solar system. So if you're going to build a spacecraft, go to these 3 places. Number 1 is Mars. Okay, so this photo on the right here, this is a really old photo. It's actually from 1976. It's from the Mars the Viking orbiters that went around Mars, 76, 77. And it kind of looks like some of the areas in Rajasthan, right? Where you have it's dry, it's like a dry desert, and then you had a monsoon that came in there, and it made these channels cut in the ground, and you can see all the drainage channels there, right? So, but this is not Rajasthan, it's Mars. And what we see on Mars is that Mars used to have liquid water all over the surface. Now we see the lakes, we see these ancient riverbeds. It's all gone now. So the Mars's atmosphere probably evaporated into space about many billions of years ago, and it's all gone now. But it used to be there. There's a little bit of evidence for a little tiny bit of water left on the surface of Mars. Not very much, but sometimes we see like these channels on the left, that left photo. Those are recent channels that were made in the last couple of years, and so that might be evidence for a little bit of water that's still left on the surface of Mars, but it's mostly pretty dry now. There's also some evidence that we've seen fossils on Mars, like fossilized bacteria. And at the bottom here, there's two photos here. The one on the top that has that green thing in there, there are some scientists who think that that is a fossilized, what we call a nanobacteria. In other words, a fossilized bug that's from Mars. Most people think that's not what it is. Most people think it's just a crystal or something like that on Mars, something that looks like a bug. But there's been a lot of debate among scientists about this. Where this came from, how we found this, is not that we brought back the rock from Mars, and it's not that we studied it on the surface of Mars, but that this rock on the bottom there, you can see it's about 1 kilogram. It's about the size of a potato. And there was an asteroid that hit Mars, and it blasted, there was an impact, and so this material came off of the surface of Mars, this meteorite, essentially, traveled through space for thousands of years, eventually landed in Antarctica. It was picked up from the surface of Antarctica. Now, Antarctica is all covered with ice. So if you're walking along the surface of Antarctica and you find a rock, where did that rock come from? It probably came from space. And so there's many meteorites all across the surface of Antarctica. This particular one, they picked it up, found it was a meteorite, and then studied some more and found that it actually was a meteorite that came from Mars. And so there is some evidence that this might be evidence of fossil or very early life on Mars, but not everyone agrees on it. So it might be just a crystal. However, finding this rock on Mars has generated a lot of interest from NASA and from across the world. And so NASA has built a number of Mars rovers to go across the surface. We have the Curiosity rover, the Perseverance rover, which are currently exploring Mars' surface and looking for past life and habitability. And so they have essentially a chemistry lab on board. They have you know, the rover and a scoop and many cameras and brushes to move the dust around, and a drill to drill into the rocks. And Perseverance actually has a drill to take some samples, which we could bring back to Earth later. It's not going to bring them back to Earth, but in the future, it could bring them back. And so it's doing this sorts of chemistry that you would do with a chemistry lab on Earth, and testing these, either looking for life or looking for past life, or looking for whether Mars used to have the right temperatures and environment to support past life. So NASA has a lot of interest in doing this. Okay, that's number one, is Mars. Number two is the moon of Saturn. So many of you may have seen Saturn through the telescope. One of Saturn's largest moon is one called Titan. After that, there's another large moon, which is a little bit harder to see, called Enceladus. And so Enceladus is really neat because you look at it, and here's a photo of it down at the bottom. And you can see that it's made of ice. So it's cold, it's pretty far from the sun, so it's made of ice. This ice is solid. But you see these plumes coming up, and these plumes are actually very large, and they have liquid water. The plumes are shooting out, it's like a geyser, and it's shooting out liquid water into space. How do you have liquid water, which is coming out from a frozen ball of ice? You can't really do that. That must mean mean there's liquid water inside Enceladus, and so Enceladus is somehow warm inside of it. It has this ocean of water inside of it, salt water, and then it's being squeezed out from Enceladus. Now, if it's warm at Enceladus now, it's probably been warm for a long time at Enceladus, and so perhaps for billions of years, there's been this warm ocean below Enceladus's ice, orbit around Saturn. So this is a really exciting place to look. This was detected by the NASA Cassini spacecraft, which was orbiting Saturn, and it returned data from Enceladus and the other moons. Cassini actually flew directly through Enceladus's plumes, and it has a sampler, which was essentially tasting the plumes, and detected that there was salts and other things dissolved in there, which gave some clues into the composition and origin of these this ocean on Enceladus. That's Enceladus. And then finally, we also have Jupiter's moon, Europa. So if you've ever looked at a telescope and seen Jupiter, probably right next to it, you saw 4 dots. And those are Jupiter's largest moons: Io, Europa, Ganymede, and Callisto. And so Europa is one of these moons. And just like Enceladus, it has an ocean below the surface, but in fact, it has an even bigger ocean that covers the whole surface. So this is kind of like as if the whole ocean on Earth were covered with ice, sort of like the North Pole. You know, the North Pole is covered with ice, but you take that North Pole ice cap and you put that around the whole Earth. That's what Enceladus looks like. So maybe you need to go down a kilometer or 10 kilometers, 50 kilometers on the surface to get into the ocean. But you can, below the surface, you can see this ocean there. And so it probably has this warm, if you have something that's warm and wet, there can be a lot of chemistry that happens in there over billions of years. And I'm going to talk a little bit more about what we're going to do with Enceladus, or with Europa, and in a future upcoming NASA mission. So those are the best 3 places to search in our solar system. And there's many places to search for life elsewhere in the universe. So you can actually do a lot of searches for life based on Earth. So here in this upper right photo, this is a photo from the Yellowstone National Park in the US. And this is where there's hot pools of hot water driven by geothermal activity. And you see that all this red stuff, this is chemistry that's happening, and this is life, and this is biology. And this is essentially like, if you have water, which is warm, there's chemistry that happens. It just starts popping out there. So you can study the areas in which life may have formed in the universe by studying how life evolves in what we call hydrothermal systems, so hot water systems on the Earth. So you can do a lot of studying for life throughout the universe by studying Earth. In our solar system, we can visit the planets in a couple of years by sending a spacecraft out there. Even the closest star, however, Proxima Centauri, sending a spacecraft like we have now might take 50,000 years, half a lakh years, to get out to Proxima Centauri. So it takes much more time than any of us have to actually send a spacecraft to a star and then bring it back. So that's far too long. What instead we do to look for life around stars is we can listen to them. We have arrays of radio telescopes. This is one in the state of New Mexico. And these are doing science, studying formation of stars and galaxies and many, many other things. But one of the other things you can do with them is listen for signals that may have been used, may have been emitted by life or other planets in space. And so you can use these radio telescopes to listen for signals, or you can just take the data that's been used for other purposes and then search through that afterwards to see, hey, is there any contamination that might be caused by a signal that could be life? Also, we can use telescopes, optical telescopes, meaning telescopes like across India, in Ladakh, for instance, is this very large high altitude telescope of India. And you can use these telescopes to detect planets, exoplanets. And these exoplanets are planets which are orbiting the other stars. And even with a small telescope, like what you have at BITS Pilani, a small Cassegrain telescope, you can use these to detect these exoplanets and measure their size, measure their position, measure how big they are, and use that to predict what temperature they are, and see if those planets would be in the same temperature zone that liquid water would be formed at, or would be stable at. And so by detecting it, we have detected thousands and thousands of planets going around other stars. And by continuing these studies, we can characterize where planets form and how many of them might have liquid water on their surface. Now, the only place we can search directly for life by actually going there is in our solar system with spacecraft. This is the only place that we can search directly for now. So I'm going to mention 3 NASA astrobiology missions. So we have 3 spacecraft missions at NASA right now, which are in operation. And I'm going to talk about those. The first one, actually, we have more than 3, but 3 of them are I'm going to talk about 3 of them. First one is the Mars Perseverance rover, then the Europa Clipper, and then the Dragonfly mission. So this is a chart of all of our missions. You can see there's a bunch of other missions. Not all of them are related to searching for life. Many of them are related to other things. But astrobiology is the big thrust of NASA's. So this is the Mars Perseverance rover. It launched in 2020 from Cape Canaveral in Florida, and it landed in 2021. It takes about 9 months to get to Mars, and it landed in Jezero Crater on Mars. And so this is about 900 kilos. That's a size of a good sized car. And it has a rover and a chemistry lab, which is searching for signs of ancient life and collecting samples of rock for possible return to Earth. So it has a drill which can pick up samples of rock and store them. So then later, another spacecraft might come and retrieve those rocks and bring them back to Earth, because it has a really good chemistry lab on board, but it's no chemistry lab that you send to Mars is going to be as good as a chemistry lab that you can have on Earth. So here's what the Perseverance rover is doing. It's been driving for essentially, hundreds of days on the surface of Mars. It's driven many kilometers on the surface of Mars, and every day there's the rover drivers at the Jet Propulsion Lab, and they plan out a route using its 3D imaging capability, and they work around the rocks on the surface and so forth to find the most interesting areas of life, interesting areas of geology and chemistry to search for, to explore the history of life. The Mars Perseverance rover is very similar in overall design and size to the Mars Curiosity rover. The Curiosity rover is in a different crater, in a different location on Mars. It's one called Gale Crater. But both of them are studying the history of water and history of habitability on Mars. And the Perseverance, or the Curiosity rover, has been there for essentially for almost 10 years now on Mars. We measure these things in sols. A sol is a Mars day. A Mars day is about 15 minutes different than an Earth day, because Mars rotates at a very slightly different speed. You can see here on this map on the left, this is a map every day of where the Perseverance rover's path takes it. You can also see that there's the helicopter on Mars. This helicopter is so cool. is amazing that we can take a helicopter to Mars, because Mars's atmosphere is 1,000 times thinner than the atmosphere on Earth. And so this helicopter is called Ingenuity. I don't know if you've seen photos of it, but it has blades which are like 1 meter across here, like that. And these blades spin up super, super fast, and they're really lightweight. And so this has these huge blades, and then when it's flying, its payload is basically something which is very, very small, something the size of a mobile. And so it has these huge blades because there's very little atmosphere on Mars. Just take this mobile around. So the Ingenuity's job is just to map out the surface, and its main job actually is a technology demonstration to see if we actually can fly a helicopter on the surface of Mars. The answer is yes. We've done really well with it, and perhaps future missions will make more use of helicopters on Mars as well. So in Jezero crater, so this is the crater which Mars Curiosity rover, which Perseverance is exploring. If you go back in time, 4 billion years ago, Mars was wet and warm. And so you had this crater there, and it had rain, and you had water going into it. And if you're at a lake, you know, the most interesting stuff where it's really messy and where it really smells bad and where there's all the muck is if you go to the center of the lake, right? That's where all the mud is. That's where everything falls into, is at the center of the lake. And so the same thing happens on Mars. You have all this rain, all this erosion, and everything falls to the center of Mars, center of this crater. And so now, billions of years later, we have a rover there, and this rover is going through essentially the middle of that crater and going through the different layers. So it's finding all the muck which was in that crater, and then it's driving up. And when you drive up, you drive through newer terrain, different layers of geology as you drive through it. And so it goes through all these different layers to explore the history and the evolution on Mars. So it's these sorts of things. This is a 4 billion year old rock on Mars, and you can see how it looks just like a mudstone that you might see on the ground in Rajasthan. This is about 1 meter across, so it's a very easy scale. And you can see the cracks. Those are cracks caused by this mud drying out in the sun. And it's exactly the same chemistry and physics which happens on Earth. It's just this happened 4 billion years ago. Okay, so that's Mars. And that's what NASA is doing at Mars right now. Second thing that NASA is doing right now is Europa Clipper. So I mentioned Europa, the moon of Jupiter, and Europa has this icy shell because it's cold on the outside. But then when you go below that shell, we think that there's this warm ocean below it. And it's probably been warm and wet for the entire age of the solar system, making it one of the richest environments in the solar system to explore, because you've had all this chemistry happening for the last 4 billion years. So let's go up there. We have you can see the different layers here. And we actually have a spacecraft. It's called Europa Clipper. It will launch in 2024. It's being built right now by the Jet Propulsion Lab and the Applied Physics Laboratory, 2 labs in the US. And it's being built right now. It will launch in 2024, and then it will orbit Jupiter for 4 years. And Jupiter is a very difficult environment to go to because there's a big magnetic field. There's lots of particles and electrons going through space that try to break your spacecraft. So there has to be a lot of shielding here. We can't get super close. We can't stay at Europa the whole time. But its prime target really is to study Europa and to study the history of the ocean, the chemistry, dynamics, its energy, its composition, and its interaction with the surface. Maybe in the future, we'll have a lander which actually lands on Europa. We haven't done that yet, but this orbiter will perhaps pave the way for that in the future. So that is the Europa Clipper mission. Finally, there's for me, maybe this is the most exciting. This is one that I didn't mention before, and this is going to the moon Titan. Now, Titan is another moon of Saturn. Titan is one of the most interesting moons in the solar system, and it's one you can easily see in a telescope. It's very large. That's why it's called Titan, because it's so big. And Titan doesn't have liquid water on it. In fact, Titan is so cold that all the liquid water turns to rocks. And if you look at this picture on the right, that's a picture which was taken by a NASA spacecraft before of the surface. And all those rocks that you see there, those are actually just ice. Those are ice, which has gotten so cold and they act like rocks, and you hit them with a hammer, they're hard like rocks. But it does have liquids on the surface. It has liquids which are ethane or methane, so CH3, CH4. And And it has a lot of chemistry going on. It has a lot of atmosphere going on. You can see the atmosphere there. You can see lots of clouds. And then it has lakes, it has sand dunes, it has mountains, valleys, and rainstorms, and tons of complex chemistry in this really thick atmosphere. So it's actually very different. It's kind of similar to the Earth in some ways, and very different from the Earth. Similar to Earth, that has the same processes, but different than Earth because it has a totally different chemistry, because it's not water chemistry, but it's liquid ethane and methane chemistry. So what NASA is working on is sending the Dragonfly to Titan. So Dragonfly is a UAV, a drone, essentially a quadcopter. Actually, it has 8 propellers though, so we call it an octocopter. And so it's going to go on a rocket, and then the rocket drops it off in the parachute. The parachute slows it down, and then its rotors turn on, and so it can fly around the surface. So this is very much like a drone that you would fly on the Earth, but the atmosphere at Titan is so thick that it's very, very easy to run an aircraft on the surface of Titan. This has a power source to power it for many years. It doesn't need solar power. And this Dragonfly mission is going to be launched in 2028, and it will spend more than a year exploring the surface and the chemistry of Titan, looking for hints to the origin of life, perhaps on Titan and elsewhere in the solar system. So Titan is, so this is maybe for me one of the most exciting missions that we have going through the solar system today. I want to mention that all these 3 NASA missions, these are funded by NASA in the US, but NASA's vision is to discover and expand knowledge for the benefit of humanity. All of the results from these NASA astrobiology missions and every other NASA mission are available for use by anybody. There's many, many people in India and across the world who use NASA data. It can be downloaded for free. All of the scientists in the US have access to the same data that anybody in India can download. And this is the missions to Mars, to Jupiter, to Pluto. You can go to the NASA website, it's called the PDS, the Planetary Data System, and you can download all of the data that anybody else, any other researcher has access to. And so I invite you to if you're interested in analyzing NASA data and doing science with it, to actually download the data and start looking at it. And of course, NASA is only one of many space agencies around the world, and one of the most exciting is, of course, the work that ISRO is doing. So I lived in Bombay for a couple of years. I lived in Bombay during when the currency was canceled, and I know I was at my office in Fort one day when I finally saw someone who had the new 2,000 rupee note. And so this is actually we didn't have any rupees then, and finally this one person had this 2,000 rupee note, and so I took a photo of it. This is the first 2,000 rupee note that I saw after the currency had come back, and so exciting to see the Mangalyaan, the Mars orbiter mission, front and center on that 2,000 rupee note. So exciting. The Mars orbiter mission, it launched in 2013. It's been in orbit since 2014. It has 2 big goals here, which are to image the surface and to search for methane. Methane is really exciting because methane is a unique molecule. It doesn't live for very long on the surface of Mars, and so if you see it, it means it was made recently, and it could be made by 2 different ways. One is by biology, and one is by volcanoes. Volcanoes give off methane, and biology gives off methane. And so if we see either of these on Mars, this will be really fantastic and interesting. We've seen these hints of these from a couple of missions from Europe and from the US. And one of the Mars orbiter mission's goals is to study the methane on Mars as well. There's also other astronomy which can be done from India. This is a picture I took. I went up to the Lonar crater, Maharashtra. And this is an impact crater, one of the best impact craters to study on the Earth. This is actually, this has been here for about 5 lakh years. You can go there, many of you may have been there. And what's really neat here is that it's into the basalt, which is volcanic rock, the same sorts of rocks which are on the surface of Mars. And it has a hydrothermal system, so there's water there and there's chemistry, and this may be the best site on Earth to study the conditions which are like ancient Mars. So there's many scientists from the US and from India and from elsewhere who are actively studying the Lunar crater, because studying this tells you about the conditions on Mars. One more thing, and then I'm going to wrap it up. I've looked at the places that you might look for life to see if it's there. One thing we don't know is how do you make life in the first place? And there's two completely different models for how this is done. Number one, maybe you build it from scratch. So if you have chemistry, and chemistry keeps getting more and more complex. First you build atoms. Those atoms turn into molecules. Those molecules turn into organic molecules. Those organic molecules turn into amino acids, and then those turn into DNA, and then those turn into life. So you can have this chain of getting more and more complex. Some of those steps are very easy. Some of those are very hard. So this is one way that you could form life on Earth. The other way that life may have come to Earth is it formed somewhere else, and then it was brought to Earth. And we call this panspermia, so moving the seeds. So the Earth actually gets hit. I showed you a picture of the Earth getting hit by this potato-shaped rock that came from Mars. The Lunar crater was formed by something many, many tons that came in and excavated that. The Earth gets hit by 40 tons of material from asteroids and comets and other planets and other solar systems every day. And so organic molecules coming along, life coming along, could move life from another system to Earth in this way. So we have these two entirely different methods, forming life from scratch on Earth or bringing it in from somewhere else. We have no idea which of these happen. They're totally different, and it's just our future work which is going to start to address, start to answer this. But it's a big mystery right now. A couple of closing thoughts. First of all, if you're looking for life, just search for liquid water, because liquid water is probably the best place best thing to search for, because if you find liquid water, that's the sorts of places that you probably would find life. Inside our solar system, there's some great places to search for life, and we're just barely starting. We have these missions that I talked about at Mars, at Europa, and at Titan, which are great places to start. So I encourage you to follow those. Outside our solar system, it's much, much, much further away. So we can't visit them. We can't go to other stars, but we can certainly get some hints and study these quite a bit by using telescopic studies from Earth. So that's all I have, and I would be happy to take some questions afterwards. Thank you so much. I'm going to stop the presentation here.
Thank you, Dr. Throop. Your talk was really interesting and insightful for all of us. Thank you for sharing these pearls of wisdom with us. So now there are a few questions we have collected from the audience. So let's dive right into it. Yeah. So one thing, like many students were asking, what was your constant source of motivation in your way of being a successful astronomer?
What was my constant source of motivation? I think it's fun. That's it. I think that scientists are very lucky because we get to study the world around us, and that's our job. We get to have questions and work to answer those questions. And the motivation is just that we are lucky to be here to explore this awesome world around us. Oh, I can't hear you.
Yeah, I'm sorry. So it's a dream of many to get an asteroid named after them, but only a few actually get bestowed with that honor. So after achieving the feat this big, how did you feel? How did your life change after that?
My life has not changed at all. It turns out, so that I'll tell you one thing, there are a lot of asteroids out there. Most asteroids do not have names. There are hundreds and hundreds of thousands of asteroids. This particular asteroid, which is named Henrythroop, is one which was discovered some time ago, and it's very I feel very honored to have it named after me. But there are many asteroids out there, and there are many more that we have not discovered yet. In fact, the more we search, the more small asteroids we find. And so there are probably millions or perhaps even billions of asteroids out there. And so there's probably an asteroid for everybody. We just need to find it.
Yeah. So as much as we'd love to continue this is all the time we have, Dr. Throop. So it was a delight hosting you. Thank you again for joining us here today. With that, we conclude the first talk of Think Again Conclave. Don't forget to join us at 5:30 p.m. for the next talk with the distinguished and renowned author Jeffrey Archer himself. Thank you.
Thank you so much. Bye-bye.